Let's be real. Applications are never really finished, are they? They're always evolving. We're adding features, fixing bugs, adapting to new business needs. But here's the thing. When your application code changes, the data it handles has to be able to change right along with it. So, in this explainer, we're going to dive deep into how modern systems pull off this constant, tricky evolution.
You know, the ancient Greek philosopher Heraclitus said, "Everything changes and nothing stands still." This isn't just some dusty old quote. It's basically the first rule of software engineering. Change isn't an occasional problem. It's the normal state of things. And that makes the ability to evolve one of the most critical, non-negotiable features of any solid system.
And that brings us right to the hero of our story today, evolvability. It's exactly what it sounds like. The principle of designing systems so that adapting to change is easy, not a nightmare. It's all about building for the future, not just for what you need today. So here's our game plan. First, we'll tackle the core challenge that change throws at us. Then we'll get into the nitty-gritty of how data is represented, going from memory to raw bytes. We'll pit text encodings against binary ones, unlock the power of schemas, see how to evolve those schemas without breaking everything, and finally, look at where this all matters in the real world. Okay, picture this. You've got a massive application. You can't just shut the whole thing down to deploy new code, right? You have to do what's called a rolling upgrade. You deploy the new version to a few servers at a time. But this means for a while, you'll have old and new versions of your code running side by side, maybe even reading and writing the exact same data. The first piece of this puzzle is what we call backward compatibility. It's pretty straightforward. It just means your brand new code can still read the old data that was written by the older code. This is usually the easier direction. Why? Well, because when you're writing the new code, you already know what the old data format looked like, so you can just teach it how to handle that old school structure. Now, this is where it gets tricky. Forward compatibility. This means your older code has to be able to read data written by your newer code. Think about that for a second. The old code is going to see data with fields and structures it has never seen before, and it can't just crash. It has to be smart enough to ignore the new stuff it doesn't understand. So let's lock this in because it's absolutely crucial. Backward compatibility, new code understands old data. Forward compatibility, old code can tolerate new data. You've got to have both if you want your system to evolve smoothly without any downtime. All right, so how does this compatibility problem actually pop up in practice? Well, it all starts with the fundamental difference between how data exists inside your application versus how it exists when you need to send it somewhere else. They're two totally different worlds. See, inside your app's memory, data is organized in these really rich, complex structures, objects, lists, trees, you name it. They're all connected with pointers and optimized for lightning-fast access by the CPU. But the moment you want to write that data to a file or shoot it across a network, all those pointers become completely meaningless. You have to translate it all into a flat, self-contained sequence of bytes. That translation from memory to bytes, that's called encoding, or sometimes serialization. And going the other way is decoding. To make all this concrete, we're going to be using this simple record as our example throughout. It's just a little JSON object, with a username, a favorite number, and an array of interests. Keep this little guy in mind, because we're about to see it get a whole bunch of different makeovers.
Let's start with the formats you probably know best, textual ones, like JSON or XML. They're awesome because they're human-readable, which is great for debugging, but they come with some sneaky little problems.
For instance, numbers can be a bit ambiguous. JSON doesn't specify precision, so a really big number can get messed up if it's parsed by something like JavaScript. They also have no built-in way to handle raw binary data, so you're stuck with clunky workarounds like base64 encoding. And of course, they are so verbose. Those field names, username, favorite number, interests, are repeated in every single record. Over millions of records, that wasted space really adds up. So, what's a better alternative? Well, have a look at this. This is our same record, but this time encoded using MessagePack, which is kind of like a binary version of JSON. It's a bit smarter, and it shrinks the size down from 81 to 66 bytes. But notice, it still includes the full text of the field names like username right there in the data. That repetition is the next thing we're going to get rid of, and that's where the huge savings are.
And this is where we take a massive leap in efficiency. We're now moving into formats that use a schema. Think of it as a blueprint for the data to strip out all that repetitive, redundant information.
And here we go. This brilliantly illustrates the core idea behind protocol buffers and thrift. Look closely. The field names are gone.
Instead, we've got these little numeric tags, 1, 2, and 3. The schema is what tells the parser that tag 1 means username, tag 2 means favorite number, and so on. Just by doing this, we've cut the size of our record almost in half, all the way down to just 33 bytes.
But believe it or not, we can go even smaller. This is our record encoded using a format called Avro, and as you can see, there's almost nothing there. No field names, no tags, nothing. It is just the raw values, one after the other. Now, to make any sense of this, the decoder absolutely must have the exact schema, because the schema is the only thing that knows the order and type of each value. This is as compact as it gets, shrinking our record to a minuscule 32 bytes. So let's just put that all together and look at the scoreboard. It's pretty dramatic, right? Our original JSON, even with all the white space stripped out, was 81 bytes. Message pack helped a bit, getting us to 66, but by using a schema, protocol buffers absolutely crushed that, down to 33 bytes. This isn't some tiny optimization. For systems that are slinging around terabytes of data, this is a total game changer.
Okay, so these schema-based formats are incredibly compact. We get it. But how on earth do they handle change? How did they give us that forward and backward compatibility we were talking about at the very beginning? This right here is the secret sauce for Avro's amazing flexibility. When you go to decode some data, the Avro library looks at two things: the schema the data was written with, we call that the writer's schema, and the schema the code is expecting right now, the reader's schema. It then puts them side by side and matches up the fields by name. If the reader expects a field that the writer didn't include, no problem. It just fills in a default value. If the writer included a field the reader has never heard of, it just gets ignored. Simple as that. And this leads to two different sets of rules for how you can evolve your data. For Thrift and Protobuf, it is all about the tags. Those numbers are sacred. You can add a new field with the new tag, sure, but you can never, ever change the tag for an existing field. For Avro, on the other hand, it's all about the field names. You can add or remove fields as long as you provide a default value for them. This matching by name approach makes it a lot more flexible over the long run.
Okay, enough theory. Let's connect all this back to the real world. Where do these choices about data encoding actually have a big impact? I really want you to pay close attention to this diagram because it shows a classic and very dangerous trap you can fall into, especially with databases. So follow along. Step 1. Some new code adds a new field, say photo URL, and writes a record to the database. Step 2, an older version of the code, which has no idea photo URL even exists, reads that same record to change something else. Step 3, the old code saves its changes, rewriting the entire record. And because it didn't know about photo URL, that field is just gone. It has been silently deleted. That's a super subtle but really critical data loss bug. And you see these exact challenges in pretty much every way data flows between systems. In databases, the data often lives way longer than the code that first wrote it, so compatibility over many years is essential. With APIs, the glue that holds microservices together, different services have to evolve independently without breaking each other. And even with asynchronous messaging, where services are decoupled, the messages they send back and forth still need a shared, compatible language to be understood. And this all brings us to a final, really important question to think about. As our systems get more and more distributed, more complex, and live for longer and longer, is a data format's ability to evolve gracefully over time ultimately more important than its raw day one performance? It's a trade-off that's definitely worth thinking about in your own work.